Welcome to the Deep Dive, where we unpack complex ideas into actionable insights for you.
It's great to be here.
Today, we're plunging into a truly fascinating and, I think, often counterintuitive aspect of human cognition. I want to start us off with a bit of a puzzle.
Okay, I like puzzles.
How can a seemingly rough rule of thumb, a simple mental shortcut, sometimes actually outperform a really sophisticated, say, 19-variable statistical model?
That sounds wrong, almost.
It sounds almost absurd, doesn't it? The very idea that having less information or maybe processing it less thoroughly could lead to better decisions. Well, it directly challenges almost everything we're taught about logic and efficiency.
You've hit on the core of it right there. That's precisely the provocative heart of today's deep dive. You see, the conventional wisdom, especially from fields like behavioral economics and psychology, has often described heuristics, those mental shortcuts we all use constantly, as cognitive flaws.
Right, they're usually framed as biases, aren't they? Things that lead our judgments astray, make us predictably irrational.
Exactly. Predictably irrational. That's the common narrative. They're presented as things that cause deviations from logical norms.
And that's what we're going to, fundamentally challenge today. Our mission in this deep dive is to explore a growing body of research that really questions this bias-centric narrative. We're going to explore the powerful idea that heuristics are not design flaws in human cognition. Far from it, actually.
Go on.
They are quite powerfully evolutionarily tuned features optimized over millennia for making decisions under very specific, often really harsh constraints. This reframing, I think, will resonate deeply with anyone who appreciates, the elegant underlying mechanisms and functional design of complex systems.
Indeed. And to really grasp this, we need to briefly step back and consider the context in which the human mind was actually forged.
Okay.
Our ancestors weren't living in neat, well-defined textbook problems with clear answers. Not at all. Their environments were characterized by profound uncertainty, immense time pressure, and very, very sparse data.
Right. Not exactly a laboratory setting.
Far from it. There was simply no luxury of computing every single probability or waiting for infinite time to gather every last scrap of information. Impossible. Instead, our minds evolved to satisfice.
Satisfice. Meaning?
It means they learned to make decisions that were good enough and, crucially, fast. Think about choosing the first usable path through a dense forest rather than spending days trying to map every single possible route. It involved leveraging bounded cognitive resources, making the best call you could with what you had, quickly.
So what might look suboptimal if you judge it by some idealized standard of rationality like, calculating every possible outcome perfectly, that same approach often excels in the wild, right? In the messy real-world scenarios where survival was everything.
Exactly. It's about being effective, not just theoretically perfect on paper. And this principle that less information can sometimes be more effective, well, that's going to be a recurring theme today.
Okay, that's a crucial distinction. So lay out the journey for us. What's the roadmap for this deep dive?
Right. We're going to take you on quite a journey today. We'll kick things off with a really vivid, real-world case study from the African Kalahari. You'll see how simple, traditional knowledge can, quite surprisingly, outperform high-tech gadgetry.
Interesting.
Then we'll dive into the scientific principles that explain phenomena like that, examining in detail how these fast and frugal heuristics can actually beat more optimized, complex strategies, especially when the environment is noisy or uncertain.
And it gets even more intriguing, you mentioned.
Oh, absolutely. We'll explore something called error management theory. This helps us understand how judgments we typically label as biased, like instinctively seeing shapes in the dark, or maybe always assuming the worst-case scenario, can in fact be perfectly rational, even vital adaptations for survival.
So biases aren't always errors.
Not necessarily. We'll dissect the ongoing debate between the traditional heuristics and biases paradigm and this newer, more nuanced ecological rationality perspective.
Okay, and then the practical side.
Yes, finally, and this is a key takeaway for you, our listener, we'll distill some very practical guidance. We want to equip you with the strategic tools to choose the right heuristic for the right job, how to effectively map problem features to the most appropriate decision strategies.
Sounds like it's about empowering us to make smarter, more effective choices in our own lives.
That's the goal, giving you a better understanding of your own cognitive toolkit. #1, heuristics, flaws, or features. The introduction unpacked.
Okay, so let's unpack this core controversy a bit more. The traditional view, the one most of us probably learned in Psych 101, right? It frames heuristics primarily as these cognitive shortcuts that introduce bias into our judgment.
That's the standard picture.
This perspective suggests that these rules of thumb are somehow inherently flawed, leading us down paths of predictable irrationality and causing us to deviate from what would be considered logically normative behavior. It basically implies our brains are making systematic errors all the time.
That's right. And it's a powerful and, frankly, pervasive view. It's significantly shaped how we understand human decision-making for decades. However, there's this rapidly growing body of research that presents a really compelling counter-narrative.
Okay, the challenge to the orthodoxy.
Exactly. This research argues that in a vast array of real-world situations, these very same simple mental strategies, often called fast and frugal heuristics or FFHs, can lead to decisions that are not just good enough, but sometimes demonstrably superior to those produced by highly complex analytical methods.
That's still the bit that feels really counterintuitive. Can you elaborate a bit more on why less information might actually be more effective sometimes? It just seems to go against everything we're taught about making rational decisions.
Well, the foundational answer lies deep in the evolutionary history of the human mind itself. Our cognitive architecture wasn't designed for the sterile, perfectly defined problems you find in textbooks or, laboratory experiments.
Right.
Instead, our minds were shaped, forged really, by environments characterized by profound uncertainty, immense time pressures, and crucially, sparse data. Limited information was the norm, not the exception.
So it's less about achieving theoretical perfection and much more about practical effectiveness in the actual world we live in. This idea of bounded rationality, where we operate within our natural cognitive limits rather than trying to process infinite data, it sounds like a very pragmatic approach.
Precisely. It is pragmatic. While it might appear suboptimal when you compare it to some idealized, omniscient standard of rationality, it often proves exceptionally effective in the wild, in those complex, messy, unpredictable, real-world scenarios where our ancestors had to survive and thrive.
Function over theoretical perfection.
That's a great way to put it. And this understanding really sets the stage for everything we're about to explore. Micro recap, one approx. 5 minutes.
Okay, just to quickly pause and recap where we are about 5 minutes in. We set up this core tension. Are heuristics, these mental shortcuts, flaws leading to irrationality as traditionally thought?
Or are they actually highly adapted features, evolutionary tools, designed for making good enough decisions quickly in uncertain, real-world environments? We've introduced the idea of bounded rationality in satisficing.
And we've hinted that sometimes using less information might actually lead to better results, challenging that classical accuracy-effort trade-off. Now, you mentioned a Kalahari case study to illustrate this.
Yes, let's dive into that. It really brings these concepts to life.
All right, to really see these ideas in action, let's transport ourselves mentally to the vast, challenging expanse of the Kalahari Desert. Picture this scene. A team of Western scientists arrives, and they are armed to the teeth with the very latest in high-tech gadgetry. We're talking advanced GPS devices, sophisticated satellite data feeds, powerful computer models crunching numbers.
Above-the-line stuff.
Exactly. Their mission, to locate, study, and understand the elusive Kalahari lions. A truly formidable task in such a harsh, demanding environment.
And then, in parallel, operating in the very same landscape, you have a group of indigenous sand Bushman trackers. They have none of that high-tech gear. Instead, they rely on centuries of inherited knowledge, their own incredibly keen senses honed over a lifetime, and generations of experience. They follow the same lions, employing these age-old tracking techniques passed down through generations.
Okay, so the natural question becomes, who do you think actually provides the more detailed, the more insightful understanding into the lion's complex movements and behaviors? The scientists with the tech or the trackers with the experience?
And here's where it gets really interesting, as you said. The surprising, almost astonishing reality is that the Bushman trackers often have a significant, undeniable edge. It's not just a slight advantage. They consistently demonstrate a superior capability in understanding the lions.
What are they doing differently?
Well, their methods, on the surface, might appear deceptively simple. We're talking about incredibly nuanced tracking heuristics. They can read a partial paw print in the shifting sand. They can interpret the subtle bend of a single grass stalk, or discern the precise pattern of alarm calls from nearby prey animals.
Tiny clues.
Exactly. And from these seemingly minimal cues, they can infer an animal's exact location, its recent activities, sometimes even its physiological state, with truly stunning accuracy. It's remarkable.
And there's actual evidence for this, right? Not just anecdotes.
Oh, absolutely. We have concrete empirical evidence. In one collaborative project, sand trackers worked directly alongside researchers monitoring lions. The level of detail they achieved in collecting data on lion hunts, their movements, social interactions, it was described by the scientists as otherwise impossible to obtain.
Wow. And how did that compare to the tech?
Well, contrast this with the GPS collars the scientists used. Those collars provided raw position data, essentially just dots moving on a map. Useful, but limited. But the trackers, they could interpret crucial context. For instance, they could tell whether a group of lions was actively stalking prey, engaged in a coordinated hunt, or maybe just traveling from one waterhole to another. The GPS alone simply couldn't reveal that kind of vital behavioral insight.
So the tech gives the what and where, but the trackers provide the why and how.
Precisely. These aren't random guesses on their part. These are what we might call natural heuristics, time-tested, finely tuned rules that have evolved and been refined over countless generations. Rules like always follow the freshest prints, or if the kudu track suddenly zigzag, a predator might be nearby.
Simple rules, but powerful.
And what's truly remarkable is that each of these rules deliberately ignores vast amounts of other potential information. The trackers aren't attempting to calculate exact trajectories or run probability models on every possible lion movement. No. Instead, their heuristics are specifically designed to zero in on the few key cues in the environment that actually matter for prediction and understanding. And the results often outperform these high-tech approaches that try to process everything.
You mentioned an anecdote from a researcher, Louis Liebenberg.
Yes, a particularly compelling one.
Yeah.
He recounts a situation where trackers in the Congo were using a handheld device called the cyber tracker, basically a simple GPS with icons to record animal signs they observed. They began noting a drastic, quite alarming decline in gorilla signs in a specific area.
Okay.
Initially, skeptical scientists relying on their own methods sort of dismissed these observations, but it was later confirmed. A devastating Ebola outbreak had, in fact, decimated the gorilla population in that very region.
So the trackers picked it up first.
Significantly earlier. What's truly remarkable is that these illiterate bushmen, relying purely on their heuristic expertise encoded in observing subtle signs, effectively discovered this devastating outbreak well before the Western researchers cottoned on. So much so that they even ended up co-authoring the scientific paper reporting the findings.
That's incredible. It powerfully demonstrates how simplicity, when it's ecologically attuned, can absolutely outperform high-tech complexity.
It really does. The crucial lesson here is one of ecological effectiveness. In an environment that is inherently complex, visually dense, often data-sparse, think thick bush, the nocturnal habits of animals, constantly shifting sand, obliterating tracks, the Bushman's evolved tracking toolkit proved to be far more effective than a purely technocratic approach that relies primarily on numerical data without that deep interpretive context.
And it's vital, you said, to understand this isn't magic.
Absolutely not. It's not ESP or some mystical ability. It's the direct outcome of a cognitive design that has been finely honed generation after generation to a very specific ecological niche. Decades, centuries even, of experience allow them to continually update and refine their heuristics based on feedback from the environment.
Can you give an example of the depth of their skill?
Sure. Consider this. A master tracker can often infer an individual lion's identity, maybe its approximate age, its sex, and sometimes even its current mood or health condition, simply from examining its footprints and spoor.
Just from tracks? How?
Well, these aren't random deductions. They come from recognizing incredibly intricate patterns. The precise depth of a print indicating weight, the exact stride length suggesting speed or perhaps injury, even the subtle smell of spoor giving clues about diet or health. And then they apply these sophisticated yet often simple if-then rules that they've learned. For example, a deep imprint means the animal is heavy, likely an adult male. These seemingly simple rules are the distillation of vast amounts of observed data and lived experience.
So in essence, the Bushmen possess what Gerd Gigerenzer and his colleagues would call a rich adaptive toolbox of heuristics specifically designed for tracking.
Exactly. They don't waste time measuring everything or trying to build an all-encompassing model of the entire ecosystem. That would be inefficient and probably impossible. Instead, they instinctively focus on the few indicators that matter most in that context. This concept of the adaptive toolbox is fundamental to our entire deep dive today.
Yeah. This real-world case isn't just an interesting story. It really primes our minds for the central question we're exploring. How can simplicity sometimes trump complexity? And more profoundly, might our own much maligned cognitive shortcuts, the very biases we often try to eliminate, actually be optimal solutions to the right problems in the right environments?
That's the core question we need to keep returning to. End of chapter recap and flashcard bullet list.
Okay, that Kalahari example is incredibly powerful. It really sets the stage. Before we move on, let's quickly solidify the key takeaways from that case study. If you were making flashcards on the Bushman versus tech scenario, what would the main points be?
Good idea. So flashcard 1. Traditional expertise can outperform high tech. Bushman trackers, using heuristics honed over generations, often showed superior understanding of lion behavior compared to scientists with GPS and models.
Right. Second point.
Flashcard 2. Heuristics focus on key cues. Their success came from using simple rules, follow freshest prints, interpret alarm calls, that deliberately ignore most information to focus on the most predictive signals. They didn't try to model everything.
Got it. Third.
Flashcard 3. Context is crucial. The trackers excelled at interpreting context.
Yeah.
Shunting versus traveling, something raw GPS data couldn't provide. Their knowledge was deeply embedded in the specific environment.
Okay, and maybe a fourth point about the Ebola discovery.
Absolutely. Flashcard 4. Simplicity can lead to discovery. Relying on observable signs, heuristic expertise, the trackers effectively detected the Ebola outbreak decline in gorillas before formal scientific confirmation, highlighting the power of ecologically attuned observation.
And the overall lesson.
The big takeaway, maybe flashcard 5.
Right.
Ecological effectiveness matters most. In complex, uncertain, data-sparse environments, the wild, evolved toolkits tailored to that niche can be more effective than generic, complex tools. It's about the fit between the strategy and the environment.
Perfect. That really crystallizes the power of simple adapted strategies in the right context. Now, how do we formalize this idea of fast and frugal heuristics?
Right. Building directly on that powerful example from the Kalahari, let's now formalize the concept we've been circling. In the late 1990s, researchers like Gerd Gigerenzer and Peter Todd, among others, formally introduced and rigorously developed this idea of fast and frugal heuristics, or FFHs.
Okay, FFHs, what's the core definition?
They are defined as mental strategies that deliberately use minimal information and minimal computation to make decisions. And yet, and this is the key part, they often achieve this with striking and sometimes quite surprising success.
It's still hard to shake that initial gut feeling, isn't it? A heuristic just sounds like a cheap hack, something you use when you can't manage the optimal full calculation. Classical rationality models absolutely reinforce this idea. They assume a direct accuracy effort trade-off, right?
Exactly. The standard logic goes, if you use less information or you put in less computational effort, your accuracy must decrease. Seems intuitively obvious.
But Gigerenzer and his colleagues argue otherwise.
Completely otherwise. They essentially turn this whole notion upside down. They systematically demonstrated, through both experiments and simulations, that in a vast number of real-world environments, the opposite is actually true. Actively using less information and relying on simpler decision rules can remarkably increase accuracy.
Increase accuracy by using less information. How?
It's not just a theoretical point. It's borne out by solid empirical evidence. One of the most compelling examples, I think, comes from a really critical high-stakes area, emergency medicine.
Okay.
Imagine patients arriving at an emergency room complaining of chest pain. Doctors face this incredibly complex and urgent decision. Is this person having a heart attack? Traditionally, identifying these high-risk patients involved complex risk-scoring algorithms. These could factor in up to 19 different variables, things like blood pressure readings, really detailed ECG results, cholesterol levels, a whole host of other clinical markers.
Right, trying to be as comprehensive as possible.
Exactly. The doctors would then compute a probability or some complex score for each patient. It seems on the surface that this exhaustive, highly detailed approach would inherently be superior. More data, better decision.
That would be the assumption.
Yet, astonishingly, a remarkably simple three-step heuristic was developed that significantly outperformed this complex 19-variable algorithm in identifying those high-risk heart attack patients.
Outperformed it, not just matched it.
Outperformed it. It wasn't some minor improvement. It was a clear demonstration of simplicity's power in this context.
Yeah.
This fast and frugal decision tree essentially boiled down to asking just 3 fundamental yes-no questions.
Only 3. What were they?
They focused on really key indicators, specific critical ECG changes, certain blood pressure readings, and the precise characteristics of the patient's pain description. Based on just these 3 simple answers, patients were triaged accordingly: low risk, go home; high risk, admit to coronary care unit immediately.
And the outcome.
The outcome was crucial. This simple heuristic caught more true heart attacks, while, importantly, sending significantly fewer false alarms patients who weren't actually having a heart attack to the intensive care unit than the intricate statistical model that considered all those 19 factors.
Wow. So it wasn't just faster, which you'd expect from a simpler rule. It was genuinely more accurate.
Exactly. It powerfully illustrates Juju Renser's point that sometimes 3 simple yes-no decisions can beat a 19-factor computation.
So why? What's the underlying reason for this? Why did the complex model fail?
The underlying why for this seemingly counterintuitive result is absolutely critical. The complex model, despite its precision on paper and its comprehensive input data, was ultimately overfitting noise and irrelevant details present in the patient data.
Overfitting, you mentioned that earlier. It means it was paying too much attention to random fluctuations.
Precisely. It was trying to account for too many minor fluctuations and correlations that weren't truly predictive of a heart attack. In stark contrast, the 3-rule heuristic effectively zeroed in on the most predictive cues, focusing only on the information that truly mattered for that specific, high-stakes decision and ignoring the rest.
And you're saying this phenomenon, simplicity outperforming complexity, isn't just a one-off fluke in this medical example?
Far from it. It's been observed repeatedly across many different domains. Simulation studies and rigorous real-world tests have consistently found that under conditions of significant uncertainty or high levels of noise in the data, or when the data itself is limited and sparse, heuristic strategies reliably shine. They prove to be robust and effective precisely where complex models often falter.
Can you give another example?
Sure. Consider another powerful FFH, the take the best heuristic.
Take the best. How does that work?
It operates on an elegantly simple principle. When you're choosing between 2 or more options, it first identifies the single most discriminating cue, the one piece of information that differentiates the options and is considered the most valid predictor. Then critically, it ignores all other information. It simply takes the best cue and makes a decision based solely on that.
That sounds incredibly frugal. Does it actually work?
Remarkably well. Take the best often matches or even beats sophisticated multiple regression models in predictive accuracy across a diverse range of datasets, from predicting professor salaries to house prices. In one comprehensive review looking across many studies, it was even found to slightly outperform standard linear regression on average when generalizing to new, unseen cases.
Slightly outperform multiple regression by ignoring most of the data. That really challenges statistical intuition. But why does this happen? What's the statistical reasoning behind a simpler model sometimes being better?
Okay, the statistical reason lies in a fundamental concept known as the bias-variance trade-off. It's a really important idea in statistics and machine learning.
Bias-variance trade-off. Break that down for us.
Imagine you're trying to model a complex relationship, but you only have a limited amount of noisy data. A very complex model, like multiple regression with many variables, has low bias, meaning it can fit the existing data very closely, capturing all its quirks. But because it's so flexible, it's also highly sensitive to the specific noise in that particular sample of data. This means if you give it a slightly different data set, its predictions might change wildly. That's high variance.
Okay, so low bias means it fits the current data well. High variance means it's unstable with new data.
Exactly.
Yeah.
Now consider a simple heuristic like take the best. It has higher bias. It's not flexible enough to capture every little nuance in the training data. It makes simplifying assumptions. But precisely because it's simple and ignores a lot of the data, it's much less sensitive to the noise in any particular sample. Its predictions tend to be more stable and consistent across different data sets. That's low variance.
Ah, I see. So it's a trade-off. The complex model is precise but potentially unstable, while the simple heuristic is less precise on the current data but more stable and predictable overall.
You've got it. In real-world situations with sparse data, or where relationships are inherently noisy and unpredictable, complex models become highly susceptible to chasing random fluctuations, getting thrown off by that high variance, and losing predictive power on new data. A simple heuristic, with its fewer parameters, keeps things robust. It essentially trades a little inherent bias, not fitting the current data perfectly, for a lot less variance, being more stable and reliable in its prediction errors.
So our heuristics might be exploiting this trade-off naturally.
They do, by deliberately ignoring small evidence, perhaps noisy or less reliable cues, and instead focusing intensely on just 1 or 2 powerful, robust cues. They significantly reduce the risk of being misled by the inherent noise and randomness that permeate most real-world environments. It's like choosing a predictable tool over a high-precision tool that sometimes goes haywire.
Let's talk about another one you mentioned, the recognition heuristic. That sounded almost absurdly simple.
It is absurdly simple on the surface. The rule is, if you're asked to compare two objects on some criterion, like which city is larger, and you've heard of one object but not the other, the heuristic says to infer that the recognized object scores higher on that criterion. So you guess the city you recognize is the larger one.
Just based on recognition alone?
Just based on recognition.
Yeah.
It sounds too basic to be effective, right?
Yeah.
And yet, it is effective if, and this is the crucial ecological condition, your recognition actually correlates with the criterion in question.
Okay, so for city size, that probably works. Larger cities get mentioned more, so we recognize them.
Exactly, because larger, more important cities tend to be mentioned more frequently in media, conversations, etc. They become more recognizable. So recognition acts as a pretty good proxy cue for city size in many cases.
And there was that experiment comparing Americans and Germans.
Yes, the classic experimental example that vividly demonstrates this less is more effect. American students were asked to judge which of two German cities was larger. Surprisingly, they actually got the answer right more often than German students did.
That's the really counterintuitive part. You'd absolutely think the Germans, with their depper knowledge of their own country, would smoke the Americans on that task.
You would. But the Americans' advantage came precisely because they recognized only a few major German cities, like Berlin, Munich, Hamburg. When faced with a choice between a recognized major city and an unknown smaller city, they always picked the recognized one, relying solely on that powerful recognition cue. The Germans, however, knew pretty much all the cities, large and small. So recognition wasn't a useful cue for them. They had to rely on other pieces of information, recall specific facts, which sometimes involved less reliable cues, or led to confusion and errors.
So the Americans' lack of knowledge actually helped them by forcing them to use a simple, robust cue.
Precisely. This less is more effect meant the Americans, with less overall knowledge, made fewer errors by consistently trusting the one powerful cue of recognition when it applied. Similar effects have been documented in other domains too, where relying on a single robust cue can outperform trying to muddle through integrating many cues of variable quality and reliability.
Okay, so taken together, these findings about FFHs, they seem to point toward a fundamentally different notion of rationality, don't they? Not just abstract logic, but something more grounded.
Exactly. It points to a new notion of rationality, one that is ecological and bounded. It emphasizes that a heuristic, or indeed any decision-making strategy, is not inherently good or bad in isolation. Its true performance, its rationality, critically depends on the match between its underlying assumptions and the actual structure of information in the specific environment it's operating within.
The fit is everything.
The fit is everything. Fast and frugal heuristics are designed, often brilliantly, to deliberately limit the information they process. They might employ a stopping rule, for instance. Is there a single clear reason to choose option A over option B? If yes, stop gathering information right now and decide. This deliberate limitation, which looks like a flaw from a classical perspective, is precisely what helps them avoid overfitting to random quirks in complex, uncertain environments.
You used an analogy earlier, the Swiss Army knife versus the heavy toolbox.
Yes, think about it. If you're out in the unpredictable, dynamic environment of the field, and you don't always know exactly which tool will fit the problem you encounter, that Swiss Army knife, with its few, well-chosen and versatile tools, may serve you far better than trying to lug around and select from a heavy, overflowing toolbox full of highly specialized instruments.
Well, in sense, you need adaptability.
G. Durenzer aptly calls the mind's repertoire of such strategies an adaptive toolbox. This toolbox isn't filled with just one supercalculator. It's stocked with various heuristics, each cleverly designed to exploit different specific regularities found in the world. So rather than functioning as a single, all-purpose logical engine, the human mind is much more like a versatile handyman, instinctively reaching for and deploying the right shortcut at precisely the right time, depending on the specific demands of the situation. Micro recap to approx. 10 minutes.
Okay, let's take another brief pause here around the 10-minute mark. We've just explored these fast and frugal heuristics like take the best and the recognition heuristic.
Right. And we saw how, counterintuitively, using less information or simpler rules can sometimes lead to more accurate decisions than complex models, especially in noisy or uncertain environments.
We discussed the overfitting problem with complex models and the bias-variance trade-off, suggesting heuristics gain robustness by accepting some bias to reduce variance.
And the less is more effect, illustrated by the city size experiment, where partial ignorance actually helped. It all points to this idea of ecological rationality, the fit between the heuristic and the environment.
And the mind as an adaptive toolbox rather than a single calculator. Okay, that sets us up nicely. But if these heuristics are so great, why do they also create what we normally call biases? That still seems like a puzzle.
It does. And that's exactly where evolutionary thinking, specifically error management theory, provides a really powerful lens. Let's dive into that. End of chapter recap and flashcard bullet list.
Before we fully transition to error management theory, let's lock down the key insights from our discussion on fast and frugal heuristics, FFHs. Flashcard time again?
That's good. Flashcard 1. FFH is defined. Mental strategies using minimal information and computation, often achieving high accuracy, especially under uncertainty. Think Gigerenzer and Todd.
Okay, 2.
Flashcard 2. Challenge to classical rationality. FFHs demonstrate that less info for it can increase accuracy, contradicting the standard accuracy-effort trade-off assumption.
3. The ER example.
Right. Flashcard 3. Case study ER heart attacks. A simple 3-step heuristic outperformed a complex 19-variable algorithm by focusing on key cues and avoiding overfitting noise. More accurate, not just faster.
4. Take the best.
Flashcard 4. Take the best heuristic. Chooses based on the first discriminating, valid 2, ignoring others. Often matches or beats complex regression, especially on new data.
5. Bias variance.
Flashcard 5. Bias variance trade-off explained. Simple heuristics accept some bias, imperfect fit to current data, for low variance, stability across data. Crucial in noisy, sparse data where complex models overfit, low bias, high variance.
6.
Recognition.
Flashcard 6. Recognition heuristic and less is more. Guessing the recognized option is larger better works if recognition correlates with the criterion. Partial ignorance, knowing fewer German cities, led Americans to better performance via this heuristic.
And finally, the big picture. Flashcard 7. Ecological rationality and adaptive toolbox. Heuristics aren't universally good-bad. Their success depends on the fit with the environment structure. The mind uses a toolbox of specialized heuristics, not one general calculator.
Excellent. That really summarizes why simplicity can be so powerful. Now, on to the paradox. If they're so good, why the biases? Hashtag check 4. Evolutionary adaptations and error management.
Right. This brings us squarely to that crucial question, the apparent paradox. If these heuristics are so incredibly useful, so adaptive, then why do they also consistently produce what psychologists traditionally catalog as biases or systematic errors in judgment? It really does seem like a contradiction on the surface.
It does. It feels like you can't have it both ways. Either they're good tools or they're flawed tools. But evolutionary theory offers a truly compelling answer here, doesn't it?
It really does. It suggests that many of these so-called biases are not, in fact, signs of a broken or flawed thinking process at all. Instead, they are the entirely predictable and often adaptive side effects of cognitive systems that have been rigorously engineered by natural selection, specifically to minimize costly errors.
Minimize costly errors.
Okay, this is the core principle of what's known as error management theory, or EMT. It's a framework powerfully articulated by evolutionary psychologists like Marty Hasselton and Daniel Nettle, building on earlier ideas.
So what's the fundamental observation of EMT?
The EMT begins with a really fundamental observation about making decisions under uncertainty, which is basically all the time in the real world. Any organism, when faced with a choice where the outcome isn't guaranteed, faces 2 primary types of errors it could make.
Okay, 2 types of errors.
A false positive, which is like seeing something that isn't actually there or reacting to a non-threat, and a false negative, which is missing something that is there, failing to detect a real opportunity or, more critically, a real threat.
Got it. False alarm versus a miss.
Exactly. Now, crucially, in the real world, these 2 types of errors, false positives and false negatives, very often have wildly asymmetric costs in terms of an organism's fitness, its chances of survival and reproduction.
Meaning one type of error is way worse than the other.
Precisely. If, over the vast time scales of evolution, one type of error was consistently far more dangerous or damaging than the other, then natural selection would powerfully favor the evolution of a systematic bias within the organism's cognitive system toward making the less costly mistake more often.
Okay, hang on. So evolution would actually build in a bias to avoid the worst error, even if it meant making the less bad error more frequently.
That's the core insight of EMT. Evolution might have inclined us, for instance, to err on the side of caution in certain situations, reflecting a kind of hardwired, better safe than sorry mentality. But in other contexts, where missing an opportunity was the bigger risk, it might have pushed us towards an optimistic bias, a sort of nothing ventured, nothing gained approach. It all depends on which strategy historically paid off most, on average, for survival and reproduction in our ancestral environments.
Can you give a classic example of this?
Absolutely. The quintessential example always used is, imagine our distant ancestors hearing a sudden rustle in the bushes nearby. Now, that rustle could be something completely harmless, maybe just the wind blowing through the leaves, or it could be a deadly predator, like a lion lurking ready to pounce.
Okay, high stakes.
Extremely high stakes. Now, according to error management theory, think about the costs of the two possible errors. The cost of a false negative, that is, ignoring the rustle when it was actually a lion leading to getting eaten, is catastrophic. Game over.
Right. Ultimate cost.
Compared to the cost of a false positive, thinking there's a lion when it's really just the wind. What's the cost there? Maybe a brief moment of unnecessary anxiety, a quick sprint to safety, perhaps a bit of wasted energy. Annoying, maybe, but trivial compared to being lunch. So the costs are hugely asymmetric. Hugely. Therefore, the optimal evolutionary solution, the strategy favored by natural selection, is a built-in bias toward assuming something dangerous is there whenever the signal is ambiguous. It's far better to have many false alarms, thinking wind is a lion, than to have even one catastrophic miss, thinking a lion is just wind.
That makes perfect sense. It elegantly explains why we instinctively jump at shadows, or why we're so quick to perceive potential dangers, or even agency, like intention, in ambiguous stimuli. It's a deeply ingrained survival mechanism.
Precisely. Our very sensory systems exhibit these kinds of adaptive biases. Take our auditory system, for instance, and a phenomenon known as the looming effect.
The looming effect.
Yes. We have a natural tendency to underestimate the time to impact of an approaching sound compared to a receding one. This means that a car horn blaring as it comes toward you or an object flying rapidly at your head is perceived as being closer and arriving sooner than it actually is, objectively speaking.
So our brain speeds up approaching sounds. Why?
This built-in perceptual bias causes us to react early, providing a crucial margin of safety. It's presumably an adaptation to ensure we never react too late to an oncoming threat. Reacting a fraction of a second too early is usually fine. Reacting a fraction of a second too late can be fatal.
And what about learning biases, like fear?
That's another great example. Think about how quickly people develop intense fear associations, especially with things that were ancestrally dangerous, like snakes or spiders. In experiments, subjects can be very easily conditioned to overestimate the connection between, say, images of snakes and something unpleasant like an electric shock. We learn that fear fast.
And the evolutionary logic there.
It's crystal clear. From evolution's perspective, it's far better to have a few false alarms, meaning developing a phobia of harmless snakes and avoiding them unnecessarily, than it is to risk missing the one truly venomous snake, even just once. The potential consequences of that single false negative error, not fearing a deadly snake, are simply too high to ignore. The bias towards rapid fear learning is protective.
Okay, so EMT explains biases related to physical threats. Does it apply to social situations, too? You mentioned mating earlier.
Oh, absolutely. EMT has been applied with significant explanatory power to complex social cognition, especially in the domain of mating, where error costs were profoundly different for ancestral men and women due to their different reproductive biologies.
How so?
Well, consider ancestral men. From a purely reproductive fitness perspective, missing a willing mating opportunity, committing a false negative error by assuming a woman wasn't interested when she actually was, meant a direct loss of a chance to pass on his genes, a huge cost in evolutionary terms.
Right, a lost reproductive chance.
Conversely, what was the cost of a false positive error for a man, assuming sexual interest from a woman when there was none? It might lead to some social embarrassment, maybe a rejection, perhaps even a slap, but critically, no lost reproductive opportunity. The evolutionary costs were asymmetric.
So what does EMT predict based on that asymmetry?
EMT predicts that men, on average, should have evolved a systematic cognitive bias toward overperceiving sexual interest from women. Essentially, a kind of built-in optimistic bias or overconfidence regarding women's romantic or sexual intentions.
And does the research support that?
Strikingly, yes. A large body of research finds exactly this. On average, men do tend to interpret friendly gestures, smiles, or even ambiguous signals from women as conveying more sexual interest than the women themselves intend those signals to convey. This bias, from an evolutionary EMT perspective, isn't a flaw. It's potentially designed to minimize the very costly error of missed mating chances over evolutionary time.
Okay, that's fascinating. Now, what about women? You said the asymmetry is reversed for them.
Yes, particularly in the domain of inferring a potential partner's commitment. For ancestral women, The costs associated with child rearing were immense. Therefore, trusting a man who wasn't genuinely committed, who might desert her after conception, posed an enormous risk. She could be left alone to raise offspring, a perilous and resource-intensive task in ancestral environments.
So the costly error for women was believing a non-committal man, a false positive on commitment.
Exactly. Believing a cad's promises when he had no intention of sticking around was potentially devastating. Therefore, women are hypothesized by EMT to have evolved the opposite bias in this domain, an underestimation bias for male commitment intentions. This translates into a healthy skepticism towards suitors' proclamations of love and devotion, designed specifically to avoid that grave, false positive error of trusting someone unreliable.
And again, is there evidence for this female skepticism bias?
Yes. Data consistently supports this too. Studies show that women, on average, are generally more cautious and discerning when inferring commitment from men's behavior, often requiring more substantial proof of devotion and long-term investment before fully trusting a partner's intentions.
So in both of these cases, male overconfidence regarding sexual interest and female skepticism regarding commitment, what looks like a bias from a purely objective, logical standpoint is actually revealed by EMT to be a deeply adaptive cognitive tilt.
Precisely. It's a cognitive strategy that likely evolved because it systematically prevented the more damaging and evolutionarily costly mistake in each respective domain, given the different reproductive challenges faced by men and women.
Hazelton and Nettle used a vivid phrase to describe this: paranoid optimist.
Yes. It's a great description of how EMP shapes our minds across different domains. They suggest our mind is often like a paranoid optimist. It's paranoid in contexts where potential danger looms large, leading us to overdetect threats like the rustle in the bushes. Yet it can be quite optimistic in other domains, like mating opportunities for men, or perhaps assessing our own abilities for future success. Positive illusions, where the cost of a little self-delusion or overreaching might be lower than the cost of missing out on significant gains or opportunities.
So what classical psychologists often perceive as a mind simply riddled with illogical biases is, from this evolutionary psychology perspective, actually a highly functional, complex pattern.
Exactly. Each bias isn't necessarily an error. It's potentially a feature, exquisitely fine-tuned by natural selection to solve a specific, recurrent ancestral problem related to survival or reproduction.
Can you give a few more quick examples of biases reinterpreted this way?
Sure. The false positive bias in threat detection, as we discussed, might give rise to superstitious beliefs or conspiracy theories in the modern world, yes. But fundamentally, it also keeps us alive by making us hyper-alert to potential dangers. Or consider the positive illusions many people hold, like having unrealistically rosy views of their own abilities or their future prospects. While technically inaccurate, these illusions might actually increase motivation, resilience in the face of setbacks, and even enhance social status, delivering tangible fitness benefits.
What about seeing patterns or agency where there is none?
That too. Our tendency to perceive intentional agency behind random events, thinking the universe is sending me a sign, or attributing strange house noises at night to ghosts rather than the plumbing, could easily be a byproduct of an overtuned agency detection system. Again, from an evolutionary standpoint, it was likely safer to mistakenly assume an agent, like a hidden enemy or predator, and be wrong, than to assume randomness and potentially miss the presence of a real intentional threat.
Gigerenzer had a simple food example too, right?
Yes. A very down-to-earth illustration of this error management principle in action. Gigerenzer proposes a simple food heuristic. If something tastes disgusting or off, spit it out immediately. Don't think, just spit.
He's sensible.
Now, this rule will inevitably cause you to waste some perfectly good bites now and then. Those are your false positives, spitting out safe food that just happened to taste weird. But, crucially, it also dramatically reduces the chance of you ingesting actual toxins or harmful bacteria, thus avoiding the potentially lethal false negative of swallowing something genuinely rotten or poisonous. The trivial cost of occasionally spitting out good food is overwhelmingly outweighed by the immense survival benefit of rarely poisoning yourself. It's a simple heuristic with a clear built-in bias, assume bad if in doubt, and it's undeniably an advantageous design feature.
So putting it all together, these evolutionary heuristics, shaped by error management, they tend to sacrifice what might be considered accuracy in a purely logical or statistical sense by introducing a systematic bias.
In return for maximizing long-term fitness optimization? Yes. They are not tuned to some abstract, idealized concept of objective truth, but rather to pragmatic, real-world goals like survival and reproduction within specific ancestral environments.
And this perspective fundamentally transforms our understanding of what cognitive bias truly means, doesn't it?
It absolutely does. What might appear suboptimal, irrational, or just plain wrong in a controlled laboratory experiment, when viewed through this evolutionary and ecological lens, often reveals itself to be precisely optimal, or at least highly adaptive, within the dynamic and uncertain game of life that our minds evolved to play. Micro recap 3 approx. 15 minutes.
Okay, hitting the 15-minute mark. Let's quickly recap error management theory. The core idea is that our biases might not be flaws, but adaptive strategies.
Right. EMT suggests that when the costs of errors, false positives versus false negatives, are asymmetric, evolution favors a bias towards making the less costly error.
We saw this with threat detection. Better to assume danger and be wrong, false positive, than ignore danger and be wrong, false negative. The Russell in the bushes example.
And sensory biases like the looming effect and learned fears. Also, social biases like men overperceiving sexual interest and women underperceiving commitment, both potentially minimizing costly reproductive errors for each sex ancestrally.
So, biases can be seen as functional adaptations, sacrificing pure accuracy for fitness. The paranoid optimist mind. What looks like an error in the lab might be smart in life.
Exactly. Now, this ties directly into the broader concept of ecological rationality, how the environment dictates whether a strategy is smart or not. End of chapter recap and flashcard bullet list.
Before we fully dive into ecological rationality, let's solidify error management theory with our flashcard approach. What are the key points?
Okay. Flashcard 1. EMT core idea. Many biases aren't flaws, but adaptations to minimize costly errors in uncertain worlds. Think Hazelton and Nettle.
2. Error types.
Flashcard 2. Asymmetric error costs. Decisions under uncertainty involve false positives, alarms, and false negatives, misses. If one error type was historically more costly, example, missing a predator, evolution favors a bias to avoid that error.
3.
Examples.
Flashcard 3. Key examples. Threat detection bias. Better safe than sorry. Looming effect. React early. Rapid fear learning. Sexual perception biases. Men overestimate interest. Women underestimate commitment. Potentially minimizing different reproductive risks.
4. The reframe.
Flashcard 4. Biases as features, not bugs. EMT reframes many biases as functional, adaptive tilts designed by natural selection, not cognitive failures. Think the paranoid optimist mind.
5.
Flashcard 5. Accuracy versus fitness. These evolved heuristics often sacrifice abstract accuracy or logical consistency in return for maximizing fitness, survival, and reproduction in ancestral environments. What works matters more than what's perfectly true.
Great summary. EMT provides a powerful why behind many biases. Now let's connect this explicitly to the environment itself with ecological rationality. Okay, so if there's one central theme that should be resonating really powerfully from our discussion so far, weaving through the Kalahari trackers, the fast and frugal heuristics, and error management theory, it's this. The effectiveness, the very rationality of any heuristic or decision strategy hinges absolutely on the environment in which it's applied.
The context is king.
Absolutely. This fundamental idea is captured beautifully by the concept of ecological rationality. This perspective asserts that no single decision-making strategy is universally best across all situations. Instead, its performance, its rationality, is entirely dependent on how well it is adapted, how well it fits to the specific structure of information within its particular ecological niche.
This idea has deep roots, doesn't it? You mentioned Herbert Simon earlier.
Indeed. This concept actually traces back to the profound insights of Herbert Simon, the Nobel laureate, often considered the father of bounded rationality. He used a famous and really elegant metaphor. The metaphor of scissors.
Scissors, how does that relate?
Simon argued that rational behavior, human rational behavior, is like a pair of scissors. It emerges from the interaction of two distinct blades working together. One blade represents the structure of the task environment, the world outside. The other blade represents the computational capabilities of the actor, our internal cognitive abilities, our heuristics.
So, just like scissors can only cut effectively when both blades work together in concert.
Human rational behavior doesn't arise solely from our internal logic in a vacuum. It emerges dynamically from that crucial fit between our mental heuristics, one blade, and the structure of the world they were shaped to navigate, the other blade.
Let's break down those two blades in a bit more detail.
Okay, so one blade is our cognitive toolbox, that whole repertoire of heuristics, biases, learning mechanisms we've been discussing. It's the set of mental shortcuts and strategies we possess. The other blade is the environmental structure itself.
Right.
This includes things like the patterns of causality in the world, the way cues are distributed, the typical frequencies of different events, the degree of uncertainty, and so on.
And evolution and learning shape one blade to match the other.
Precisely. Over the vast stretches of evolutionary time, and also through individual learning within a lifetime, our heuristics, the cognitive blade, have been precisely honed and calibrated to exploit specific regularities within those environments, the environmental blade. When we operate within those familiar ecological contexts where the tool fits the task structure, our decisions can be remarkably sound, efficient, and adaptive.
But the mismatch problem.
Exactly. But critically, when we are thrust into evolutionarily novel or artificially contrived settings, like many abstract laboratory experiments, or perhaps navigating the complexities of modern financial markets which didn't exist ancestrally, those very same heuristics, normally so effective, might suddenly misfire because the structure of the new environment doesn't match the conditions they were designed for. The blades no longer align.
This brings us to another key distinction you mentioned earlier from the statistician Leonard Savage. Large worlds versus small worlds. How does that fit in?
It fits perfectly. Our ancestors, for the vast majority of human history, lived and made decisions almost exclusively in what Savage termed large worlds.
Define large world again.
Large worlds are situations characterized by fundamental uncertainty, where not all possible outcomes, consequences, or their probabilities are known or even knowable in advance. Think about crucial ancestral decisions like choosing a mate, foraging for food in a patchy environment, navigating complex social alliances, or hunting unpredictable prey in a constantly shifting landscape. In these kinds of large worlds, calculating a truly optimal answer is often impossible, even in principle. There's just too much unknown.
And that's where heuristics shine.
Exactly. In these large worlds, optimization is frequently impossible or computationally intractable. So heuristics that efficiently make do with limited information that satisfies rather than optimize inherently have the edge. They provide robust, good enough solutions quickly.
And the contrast is the small world.
Yes. Contrast that with a small world. A small world is neatly defined, closed, and well-specified, like a game of chess with its fixed rules, or a standard textbook probability problem, or perhaps a constrained engineering problem. In these situations, all the relevant variables are known, the rules are clear, and exhaustive calculation or optimization can actually work because all the necessary information is available and the structure is stable.
And Savage himself made this distinction clear.
He did. Savage, despite being a pioneer of Bayesian decision theory, often used as a benchmark of rationality, was keenly aware of this distinction. He explicitly warned that highly precise tools like Bayesian logic and optimization theory, while excellent for analyzing small worlds like lotteries or abstract probability puzzles, may fundamentally fail or be misleading when applied to the inherently messier, more uncertain reality of real-life large-world problems.
And you're saying modern research backs this up. When we test people.
Yes, contemporary human decision-making research is increasingly rediscovering and emphasizing this very point. Many of the cognitive biases that psychologists have documented over the years appear most prominently when people are tested using abstract small-world norms. For example, when they're asked to apply complex Bayesian formulas to decontextualize statistical data presented as probabilities.
But if you change the presentation.
Exactly. Here's the crucial part. If you present the exact same underlying information, but format it in ways that more closely mimic natural ancestral environments, like using natural frequencies 10 out of every 100, instead of abstract probabilities 10%, or embedding the problem within concrete, familiar cases or stories, people's performance often improves dramatically. They start reasoning much closer to what would be considered optimal or Bayesian.
So it suggests the heuristics aren't broken, they just need the right input format.
Precisely. In essence, when placed in the proper ecological context, using information formats they evolved to handle, our heuristics often reveal themselves to be profoundly rational in an ecological sense. The rationality lies in the fit.
The bias-variance trade-off comes back in here too, right?
Yeah.
How does the environment influence that?
Yes, the bias-variance trade-off provides a very useful statistical lens to understand ecological rationality. Environments that have limited data, high noise, or high unpredictability inherently punish complexity.
Why?
Because in those environments, a complex model, low bias, high variance, is very likely to overfit the noise, latching onto spurious patterns in the limited data it sees, leading to poor predictions on new data. A simple heuristic, however, higher bias, low variance, by its very nature, doesn't try to capture every nuance. It accepts some bias, But because it's less flexible, it enjoys low variance. It remains stable and robust even when data is sparse or noisy. In conditions of noise or paucity of examples, it's often the variance component of the error that dominates. Simple heuristics minimize this variance error.
So noisy environments favor simple, low-variance strategies, and there's empirical evidence for this specific link.
Absolutely. Specific findings confirm this. Studies have shown that the more noise in the observations, the more likely a simple heuristic like take the best will outperform more flexible strategies. And crucially, if observations are sparse, simple heuristics are likely to outperform general, flexible strategies. The environment dictates the optimal point on the bias-variance spectrum.
It explains why ignoring information can be smart.
Exactly. This is precisely why a heuristic that consciously ignores information can paradoxically be more accurate in a large, uncertain world. It deliberately forgoes chasing every apparent pattern in the noise, and in doing so, avoids being misled by randomness and spurious correlations. It bets on simplicity and robustness.
Can we see this ecological rationality playing out in other real-world domains beyond tracking or medicine?
Oh, yes. The illustrations are abundant across various fields. Take marketing, for example. Remember that heuristic we mentioned? Classifying a customer as inactive if they haven't made any purchases in, say, 9 months. This seemingly trivial rule actually outperformed a sophisticated quantitative predictive model when it came to forecasting which customers had genuinely churned or stopped being active.
Why did the simple rule win?
Because it succeeded by keying in on the single most relevant, robust factor, long-term inactivity, and it avoided getting confused by less reliable or noisy data points that the complex model tried to incorporate. It fit the ecology of that specific prediction task.
And the finance example with Harry Markowitz.
Right. Nobel laureate Harry Markowitz, the guy who literally invented complex mean variance optimization theory for building efficient investment portfolios, a cornerstone of modern finance. Yet, it's widely reported that when it came to investing his own retirement funds, Markowitz himself used an incredibly simple one heuristic, meaning he simply allocated his money equally to each of the available investment options, 1 divided by n options. No complex calculations, no estimating correlations or expected returns, just divided equally.
That sounds almost irresponsible compared to his own theory. How did it perform?
Amazingly well. When researchers later rigorously compared this simple 1n rule to dozens of highly optimized, sophisticated portfolio allocation algorithms using historical market data, the 1n rule consistently held its own. In fact, none of the complex models reliably beat the simple 1n rule in out-of-sample returns over long periods.
Why would that be? Why didn't the optimized models win?
Because the optimized models required vast amounts of historical data to accurately estimate all the necessary parameters, expected returns, variances, correlations, and these estimates are notoriously unstable. They change over time. The complex models were often thrown off by unpredictable regime changes in the market, overfitting to past patterns that didn't hold. The 1n rule, however, uses no estimation at all. It ignores all historical data in that sense, making it remarkably robust through changing, unpredictable market conditions. Its simplicity was its strength in that uncertain environment.
And this pattern even extends into areas like machine learning.
Yes, indeed. Consider the naive Bayes classifier. It's a widely used algorithm in machine learning for tasks like spam filtering or text classification. It makes a statistically naive, even blatantly incorrect simplifying assumption. It assumes that all the input features or variables are completely independent of each other.
Which they almost never are in reality.
Exactly. It introduces a strong bias in a statistical sense. Yet, despite this glaring simplification, naive Bayes often rivals or even outperforms far more elaborate, theoretically sophisticated classifiers in many practical, real-world tasks. Why? Because its inherent bias actually acts as a powerful form of regularization. It prevents the model from becoming too complex and overfitting the data, especially in high-dimensional problems where you have many input features but maybe limited training examples. The bias keeps it simple and robust.
So these examples powerfully underline that the optimal strategy isn't universal. It's entirely dependent on the specific ecology of information available in the task environment. A strategy that seems incredibly simple, even naively so on paper, can indeed be the optimal choice in a complex, shifting, or low-data real-world environment.
Precisely. From an evolutionary perspective, our entire cognitive toolbox was forged within these kinds of ecological constraints.
Steven Pinker's work comes in here too, right? With the idea of domain-specific modules.
Yes. Steven Pinker, in his influential book, How the Mind Works, emphasizes this adaptive ecological view by arguing that the human mind likely consists of numerous domain-specific modules. Each module is functionally specialized for processing certain types of content or solving certain types of ancestral problems, whether it's understanding physical objects, navigating social exchanges, recognizing faces, acquiring language, and so on.
And each module uses its own specialized heuristics.
Exactly. Critically, each of these specialized modules employs heuristics that are precisely attuned to the specific informational structures and challenges within its particular niche or domain.
Like the cheater detection example.
That's a classic one. We possess an incredibly effective cheater detection heuristic that seems to automatically kick in during social exchange situations. This makes us surprisingly good at logical reasoning when a problem is framed as detecting someone breaking a social rule or contract, a context that held immense evolutionary salience for our ancestors, who needed to cooperate but also avoid being exploited. Yet we might struggle significantly with the exact same underlying logical structure when it's presented as an abstract, decontextualized puzzle, like the Wasson selection task. Our logic isn't abstract, it's ecologically tuned.
Or catching a ball.
Another great example is our intuitive physics module. It allows us to perform seemingly complex feats like catching a fly ball. We don't consciously calculate the parabolic trajectory using Newtonian physics. Instead, we rely on a simple heuristic like the gaze heuristic.
How does the gaze heuristic work?
You simply move in such a way as to keep the angle of the ball's optical trajectory relative to the background constant, or perhaps keep it appearing to rise at a constant velocity. It's a beautifully simple sensoromotor rule that effectively solves the complex calculus problem on the fly, allowing us to intercept the ball without ever consciously performing any calculations. It exploits irregularity in the physics of projectiles relative to a moving observer.
Pinker argues convincingly, then, that we should view these mental algorithms not as failures simply because they don't apply universally across all domains,
but rather as evolution's ingenious engineering solutions to specific recurring adaptive problems. He points out that everyday common sense inference itself is necessarily heuristic. There isn't some hidden supercomputer inside our heads performing flawless, exhaustive logic behind the scenes for every little thing. All we have, fundamentally, are these incredibly clever, evolved shortcuts.
So when our reasoning appears to falter in contrived laboratory tests,
it's often, Pinker argues, because the test is essentially yanking a highly specialized heuristic completely out of its ecological comfort zone, asking it to perform a task it wasn't designed for. The fault, in this ecological view, is not necessarily with the mental tool itself, but rather with applying the wrong tool to the task at hand, or judging it against an inappropriate standard.
This ecological rationality perspective, then, leads us towards a crucial reconciliation, doesn't it, between the traditional heuristics and biases tradition of Kahneman and Tversky and this adaptive view from Jigrenzer, Kosmides, Kubi, Pinker, and others.
Yes, it offers an important synthesis. The ecological rationality camp doesn't deny that people systematically deviate from the norms of formal logic or probability theory in certain situations. Those deviations, those biases, are genuine, well-documented phenomena.
But they recontextualize them.
Exactly. They recontextualize them by asking why they occur and whether they might serve a function. They argue that the ultimate benchmark for rationality shouldn't always be abstract adherence to the laws of formal logic or probability theory in a vacuum. Instead, the benchmark should often be actual success and adaptiveness within the organism's relevant environment. By that measure, many of what we've often labeled as fallacies or biases might in fact be remarkably efficient and successful strategies.
And this is supported by findings where heuristics that seem to violate classical rationality actually lead to better outcomes.
Yes, even Daniel Kahneman himself, the Nobel laureate often associated with the biases view, acknowledged later in his career that he was surprised to find that in many real-world prediction tasks, fast heuristic methods won against slower, more formally analytic approaches. The core insight, then, becomes understanding when a particular heuristic is perfectly well-matched to its environment and likely to succeed, and crucially, when it is likely to be mismatched and potentially lead us astray.
The language of the heuristic matters too, you said.
Immensely. This concept of the mind having a preferred language or format for processing information is vital. If you ask people to reason using an evolutionarily alien format, such as abstract probabilities or percentages like a 5% chance, they might appear irrational and make systematic errors like base rate neglect. But if you ask the exact same underlying statistical question, but present the information in a more natural frequency format, for example, 1 out of 20 people, or embed it within a familiar story context, their performance often improves dramatically.
Why? Because you've given the cues it evolved to use.
Precisely, because you've provided the ecological cues, the input format, that our heuristics evolved over millennia to process effectively. You're speaking the mind's native language, so to speak.
So summing up ecological rationality, our heuristics are like evolved instincts of reason. They're not general-purpose problem solvers.
But highly specialized niche problem solvers.
Exactly.
Each heuristic is a specific design feature that cleverly exploits a particular structure or regularity found in a certain domain or environment. When that specific environmental structure is present, the heuristic operates with lightning speed and impressive effectiveness. However, when that structure is absent, or when the heuristic is confronted with a novel abstract problem it wasn't designed for, it can indeed mislead. And that's precisely when we observe and label the resulting systematic error a bias.
So appreciating this critical context dependence is what allows us to move beyond simply labeling human thinking as inherently biased or fundamentally irrational.
Yes. Instead, we begin to see human cognition as comprising a rich collection of ingenious mental tools, each superbly adapted to particular kinds of challenges. It's much like, going back to the analogy, a bird's wing. A wing is perfectly adapted for flying, a marvel of evolutionary engineering for that purpose, but it's utterly unsuited for swimming. To judge the wing's rational design, we absolutely must observe it in its intended environment, in the air, not submerged in water.
And so too with our heuristics.
So too with heuristics. When judged within their proper ecological context, the environments and tasks they were shaped for, they don't make us irrational. They make us incredibly smart, adaptive, and efficient. They are the bedrock of human intelligence. Micro recap for approx. 20 minutes.
All right, we're about 20 minutes in. Let's quickly synthesize the core ideas of ecological rationality. It's all about the fit between the heuristic and the environment, isn't it?
Exactly. No strategy is universally best. Rationality depends on the match. Simon's scissors metaphor captures this beautifully. Cognitive tools are one blade, environmental structure the other.
We contrasted large worlds, uncertain, real life, where heuristics excel, with small worlds, defined like games, where optimization works better. Our minds evolved for large worlds.
And we revisited the bias-variance trade-off. Simple heuristics minimize variance error in noisy, sparse environments. Even if they have some bias, complexity gets punished by overfitting noise.
We saw real-world examples, marketing churn prediction, Markowitz's 1N investing, naive Bayes in machine learning, where simple biased rules outperformed complex ones due to robustness.
And Pinker's idea of domain-specific modules using tailored heuristics like cheater detection or the gaze heuristic for catching balls, they're engineering solutions, not flaws.
This leads to a reconciliation. Biases aren't just errors, but often heuristics operating outside their evolved context, or adaptations shaped by error management. The benchmark should be ecological success, not just abstract logic.
Right, and performance improves dramatically when information is presented in ecologically valid formats, like frequencies. Heuristics are niche problem solvers, smart in their domain, like judging a wing in the air, not water.
Okay, great summary. This sets us up perfectly for the final synthesis. How do we balance the heuristics as adaptive tools view with the undeniable reality that they do sometimes lead to errors and biases? End of chapter recap and flashcard bullet list. Before we fully move to that synthesis, let's capture ecological rationality on our flashcards. Point 1.
Flashcard 1. Ecological rationality defined. Rationality isn't absolute, but depends on the fit between a decision strategy, heuristic, and the structure of the environment. Context is key.
2. Simon's scissors.
Flashcard 2. Simon's scissors metaphor. Rational behavior needs both blades. Cognitive capabilities, heuristics, and environmental structure. Success comes from their interaction.
3.
Flashcard 3. Large versus small worlds. Heuristics excel in large worlds. Uncertain, real-life, sparse data where optimization fails. Formal logic optimization work best in small worlds. Defined, stable, full info. We evolved in large worlds.
4. Why heuristics win sometimes.
Flashcard 4. Bias, variance, and robustness. In noisy, sparse environments, simple heuristics outperform complex models by minimizing variance error, avoiding overfitting, even if they have more bias. Robustness trumps precision.
5. Real examples.
Flashcard 5. Real-world examples. Marketing churn, simple rule beat model. Markowitz's 1N, equal allocation beat optimization.
Yeah.
Naive Bayes, simplistic classifier works well. All show simplicity's power in the right ecology.
6. Mind design.
Flashcard 6. Domain-specific modules in Pinker. The mind uses specialized modules with heuristics tuned to specific problems, social exchange, physics. They are evolutionary engineering solutions, not general logic failures.
7. Reconciling views.
Flashcard 7. Reconciling paradigms. Ecological rationality reframes biases. They often arise from heuristics mismatched to the task environment or judged by inappropriate small world norms. Success in the environment is the better benchmark. Performance improves with ecologically valid information formats, for example, frequencies.
Perfect. Ecological rationality gives us the framework for understanding when and why heuristics work. Now, how do we integrate this with the reality of cognitive biases?
Okay, this brings us to a really crucial point of intellectual resolution, one that attempts to bridge the apparent divide we've been discussing, the divide between how we view human cognition. The debate between the traditional heuristics and biases view and this adaptive heuristics or ecological rationality view has often been framed, perhaps overly simplistically, as a kind of pessimistic versus optimistic take on human nature.
Right. Like, are our mental shortcuts mostly just leading us astray? Meaning we need constant debiasing efforts in statistical education, as maybe the Kahneman and Tversky tradition might emphasize?
Or, conversely, are these shortcuts, on the whole, remarkably well adapted, with the errors being relatively rare or perhaps even instructive, suggesting maybe we should trust our instincts more often, as perhaps Renzer and the ecological rationality camp might argue?
It often feels like you have to pick a side.
It can feel that way. But I think the most intellectually satisfying answer, and certainly one that resonates deeply with a rational analytical mind, is that both perspectives actually hold significant truth. They aren't necessarily mutually exclusive. Rather, they often operate at different complementary levels of analysis.
Oh, wait, how so? How can both be true?
Well, let's start by acknowledging the undeniable truth from the classic perspective. The extensive catalog of documented cognitive biases, things like systematic overconfidence, the availability heuristic making us overweight vivid events, anchoring effects pulling our estimates, framing effects, changing our choices based on wording, and so on. This catalog unquestionably demonstrates that humans are not automatically rigorous logical machines.
We're not Vulcans.
Definitely not. This is undeniably true. People commit logical fallacies, we violate fundamental axioms of probability theory, and we do so in highly predictable ways. We're not perfect calculators operating in a vacuum.
Okay, so the biases are real for the adaptive view.
The adaptive view doesn't just stop there at documenting the errors. It pushes further and asks the crucial question, why do those errors occur? And in asking why, it frequently uncovers a systematic, principled, often evolutionary rationale behind them. You see, the traditional heuristics and biases paradigm tended to evaluate human decisions primarily against abstract normative criteria, like the strict rules of Bayesian probability or formal logic, and it often labeled any deviation from these abstract norms as a cognitive illusion. For example, neglecting statistical base rates in favor of a compelling individual story is indeed a fallacy by logical standards.
Right, but the ecological view offers a different benchmark.
Exactly. The ecological rationality paradigm offers a vital counterpoint by noting that in our actual natural environments, the kinds of environments we evolved in, sample sizes are often inherently small, information is almost always incomplete and noisy, and feedback can be delayed or ambiguous. In such messy, uncertain conditions, relying on a single vivid case study or trusting a strong emotional impression might actually be far more useful and adaptive in practice than trying desperately to compute an elusive statistic that simply isn't available or reliable in that context.
So the standard of judgment should be different.
Proponents argue yes. Heuristics in this light shouldn't be judged solely by their internal consistency with abstract formal logic, but rather by how effectively they actually work in achieving goals in the real world. Renzer puts this very plainly. Instead of asking if a heuristics outcome aligns perfectly with some textbook formula derived from probability theory, we should ask, does this heuristic typically lead to successful pragmatic outcomes for the organism in its environment?
And the answer is often yes.
And quite often the answer is indeed yes, which is precisely why evolution, in its relentless drive for functional efficiency, likely kept these heuristics around in our cognitive toolbox. They work, on average.
Steven Pinker had that analogy comparing cognitive biases to visual illusions, right? How does that help synthesize these views?
It's a brilliant analogy, I think. Pinker likens cognitive biases to well-known visual illusions, like the Muller-Lyer illusion, where two lines of the same length appear different because of the arrows on their ends. These illusions are fascinating because they reveal the intricate, hidden workings of our perceptual heuristics, the shortcuts our visual system uses to rapidly interpret the 3D world from ambiguous 2D retinal images. They show us instances where those normally reliable heuristics misfire, typically when presented with an artificial 2D image that contains misleading depth cues that wouldn't occur naturally.
But we don't conclude our vision is fundamentally broken because of illusions.
Exactly. We don't conclude that our eyes are generally useless or fundamentally flawed just because we occasionally get tripped up by an optical illusion on paper. Instead, we recognize that our visual system is exquisitely optimized for interpreting a real 3D world that has certain typical lighting conditions and perspective cues, and it's not specifically optimized for deciphering deliberately misleading trick drawings on a flat piece of paper.
And the analogy to cognitive biases.
Similarly, Pinker and others suggest that many of the cognitive biases observed in abstract lab settings are often simply cases of our powerful cognitive heuristics being taken out of their element, applied in contexts or to problems they weren't originally designed to handle. The illusion reveals the mechanism, but it doesn't invalidate the mechanism in its proper context.
And the language of our intuition, the format of information, plays a role here too in bridging the gap.
Yes, absolutely. We touched on this with ecological rationality. Our intuition for probability, for example, functions far, far better with concrete frequencies, like thinking 1 out of 20 people will experience this, than with abstract probabilities, such as there's a 5% chance.
Because frequencies are what we encountered historically.
That's the argument. Historically, our ancestors primarily encountered statistical information in the form of frequencies observed through direct experience, seeing how many hunts were successful out of the last 10, or how many people in the tribe got sick after eating a certain plant. They didn't encounter decimals or percentages. So once problems are framed in an ecologically natural way, using formats that our heuristics evolved to understand, people's performance often approaches surprisingly optimal levels. This strongly indicates that the underlying heuristic itself was perfectly fine, often quite sophisticated. We just needed to present the question in the right ecologically valid language for it to properly engage and process the information.
Okay, so biases are real, but often have adaptive roots or are context dependent. Does this synthesis also acknowledge genuine limitations, though? It's not saying humans are perfectly rational even in an evolutionary sense.
No, absolutely not. That's another crucial point of synthesis, acknowledging inherent trade-offs and genuine limitations. It's not the claim that humans are perfectly rational agents, even in evolutionary terms. We undoubtedly carry cognitive kludges, imperfections, and limitations, legacies shaped by the messy contingent process of path dependence in our evolutionary history. Evolution doesn't build perfect designs from scratch. It tinkers with what's already there.
So some biases might just be suboptimal baggage.
It's quite possible. Some biases may indeed be evolutionary baggage, quirks left over from past adaptations, or perhaps the unavoidable negative side effects of heuristics that were, on balance, net beneficial for survival, but still suboptimal compared to some theoretical ideal. The adaptive view doesn't claim that every single observed bias is perfectly optimal in every conceivable context. That would be Panglossian. What it does argue is that many, perhaps most, of the well-documented biases have very principled functional reasons behind their existence, often linked to error management or ecological fit.
And, crucially, knowing those underlying reasons can actually help us manage our decisions more effectively in the modern world.
Yes, that's a key practical implication. If I understand why I might be biased in a certain way, I can manage it better. For instance, if I know that I'm systematically biased toward optimism when planning complex projects, the well-known planning fallacy, I can recognize that this might be rooted in evolutionary pressures, perhaps favoring optimistic motivation or social signaling. Yes, we can do this. Armed with this self-awareness, I can then consciously correct for it in critical tasks, perhaps by deliberately adding a buffer, maybe doubling my initial time estimates for a project, without simply concluding that my brain is inherently irrational or broken.
So understanding the why enables a more nuanced approach to debiasing.
Exactly. It allows for a more nuanced and constructive approach. It's not necessarily about trying to eliminate the underlying heuristic altogether, which might be impossible or even counterproductive if it serves useful functions in other contexts. Instead, it's about becoming more aware of our cognitive tendencies and then discerning if a particular heuristic is being applied in an appropriate context for the current task. If it seems mismatched, we can then either try to adjust the environment itself to better suit the heuristic, like changing the information format, or we can consciously choose to complement or override the heuristic with a simple external tool, like a checklist, a second opinion, or a more formal analytical method when the stakes are high.
The debate is often simplified, as you said, into Kahneman versus Gigerenzer. How would you summarize their core agreement and disagreement in light of this synthesis?
Well, despite how it's sometimes portrayed as a stark opposition, both of these hugely influential thinkers would readily agree on the fundamental point. The human mind inherently relies on heuristics to navigate the world. That's not really in dispute.
So where's the difference in emphasis?
Kahneman's work, particularly his collaboration with Tversky, primarily focus on meticulously documenting the instances where these heuristics lead us systematically astray from the norms of classical rationality, often causing real-world suffering through things like poor financial decisions, medical misjudgments, or policy errors. His emphasis, therefore, tends to be on the critical need for awareness of these biases, for cultivating statistical literacy, and for engaging in more careful, deliberate System 2 thinking to override flawed intuitions when necessary.
And Judrenzer's focus?
Judrenzer, conversely, tends to emphasize how frequently these same heuristics serve us remarkably well, especially within their ecologically appropriate contexts. He strongly critiques the practice of judging human rationality solely against abstract, often unrealistic, small-world benchmarks. He argues that calls for achieving unbounded or perfectly logical, omniscient rationality are both unrealistic, given our cognitive limits, and potentially misleading, as they might cause us to undervalue the power of effective heuristics. He cautions that comparing human cognition to an idealized, godlike Bayesian supercalculator inevitably makes us look hopelessly irrational.
Whereas if you change the benchmark.
Right. Whereas if you consider rationality with respect to the specific environment and its inherent constraints, ecological rationality, our cognitive abilities often look quite good, sometimes even brilliant in their efficiency and robustness. His focus is on understanding the adaptive toolbox and promoting tools that work with our heuristic strengths.
So for you, our rationalist listener wrestling with these ideas, the synthesis is really critical.
It is, because human cognition is simultaneously both incredibly powerful and undeniably fallible. And much of its power, paradoxically, comes directly from its ingenious use of simplifications. The ultimate takeaway, I believe, isn't to uncritically idolize every gut feeling we have, nor is it to dismiss all our intuitions as merely bias-prone cognitive errors.
Instead,
the goal is to cultivate the ability to critically analyze the crucial match between the heuristic being triggered and the specific context you're operating in. Our minds are exquisitely optimized for certain kinds of conditions, dealing with medium-sized data sets, information presented in familiar formats like frequencies or narratives, content that is meaningful and holds evolutionary salience. In those conditions, our heuristic intuition can be absolutely superb, fast, and accurate.
but we need to be wary when conditions change.
Exactly. But when conditions change dramatically, for instance, when we're dealing with very large abstract statistics, counterintuitive probabilities, or completely novel abstract problems, unlike anything faced ancestrally, then we should exercise healthy caution. In those situations, it's wise to be wary of relying solely on intuition and perhaps consciously supplement it with more formal, analytical methods, external checks, or structured decision processes.
It comes back to Herbert Simon's vision again.
It really does. This synthesis beautifully echoes Herbert Simon's foundational vision of bounded rationality. We are neither fundamentally irrational demons destined for constant error, nor are we omniscient gods capable of limitless calculation. Rather, we are resource-rational beings, intelligently making do, doing the best we can with inherently limited time, limited knowledge, and limited computational power in an incredibly complicated and uncertain world. And often, the heuristics we use are the smartest way to do that. Micro recap 5 approx. 25 minutes.
All right, roughly 25 minutes in, let's synthesize the synthesis. We've reconciled the biases and adaptive tools views.
Yes. The synthesis acknowledges biases are real. We're not perfect logic machines, but asks why they exist. Often, there's an adaptive rationale rooted in error management or ecological fit.
The benchmark matters. Judging heuristics by abstract logic, small worlds, makes them look flawed, but judging by real-world success, large worlds, often shows their effectiveness. Pinker's visual illusion analogy was key here.
And the language or format of information is critical heuristics work better with ecologically valid inputs like frequencies.
We also acknowledged real limitations and evolutionary kludges. Not every bias is perfectly optimal.
Right, but understanding the why behind a bias allows for nuanced debiasing, managing the heuristic by understanding its context, not just trying to eliminate it.
It balances Kahneman's focus on errors and the need for deliberation with Judrenzer's focus on heuristic effectiveness and ecological rationality.
Ultimately, it paints a picture of bounded rationality, where resource-rational beings using a toolbox of heuristics powerful in their niche but fallible outside it. True rationality involves knowing which tool to use when,
Perfect. This leads directly to the practical application. How do we actually choose the right tool from the toolbox for a given task? End of chapter recap and flashcard bullet list. Before we get to the practical guide, let's lock down the heuristics versus biases synthesis with flashcards. Point 1.
Flashcard 1. Both views hold truth. The biases view, Kahneman, correctly identifies deviations from formal logic. The adaptive view, Jitterenzer, correctly asks why and finds functional reasons, ecological fit, error management. They operate at different levels.
2. Benchmarks.
Flashcard 2. Benchmark matters. Judging by abstract logic highlights flaws. Judging by real-world effectiveness, ecological rationality, often reveals heuristics as successful strategies.
3. Illusions analogy.
Flashcard 3. Pigger's visual illusion analogy. Cognitive biases are like visual illusions. They reveal heuristic mechanisms by showing where they misfire, often in artificial context, but don't invalidate the heuristics' effectiveness in its proper ecological niche.
Format length.
Flashcard 4. Information format is key. Heuristics work better with ecologically valid formats. Example, frequencies versus probabilities. Performance isn't fixed. It depends on how information is presented.
5. Limitations exist.
Flashcard 5. Acknowledge trade-offs and limits. The adaptive view doesn't claim perfection. Some biases might be evolutionary baggage or suboptimal side effects. We have kludges.
6. Nuanced debiasing.
Flashcard 6. Nuanced debiasing. Understanding why a bias exists allows for better management, checking context, adjusting the environment, or supplementing with tools rather than just trying to eliminate the heuristic.
7. The big picture.
Flashcard 7. Bounded rationality revisited. The synthesis supports Simon's view. We're resource rational, using limited resources effectively via heuristics. True rationality is about adapting strategy to context, not just calculation.
Excellent. That provides a balanced, sophisticated understanding. Now, let's make it actionable. How do we apply this toolbox mindset in practice?
Okay, now let's really transition from these fascinating theoretical insights to their direct practical application. Because understanding is great, but being able to use this knowledge is even better. The core takeaway from everything we've discussed boils down to this. The key to making more effective decisions isn't just knowing about heuristics, but developing the skill to consciously map the features of a specific task or decision environment to the most appropriate heuristic strategy.
So, moving beyond just reacting with whatever intuition pops up first, or defaulting always to exhaustive analysis.
Exactly. Instead of those defaults, a truly savvy decision maker, what some might call a meta-rational mind, will consciously survey the problem landscape and then deliberately choose the optimal tool from their adaptive toolbox, selecting the strategy that best fits the specific demands and constraints of the situation at hand.
This sounds like exactly what our analytically minded listeners would appreciate, a framework for choosing how to think.
Precisely. We can actually outline a practical guide for selecting heuristics, essentially creating a kind of heuristic for choosing your heuristics.
Okay, let's hear it. Where do we start?
Step 1 is always identify your environment. Ask yourself critically, is this situation more like a large world problem or a small world problem?
Remind us of the distinction again.
Large world problems are characterized by significant uncertainty, being open-ended, maybe having low or unreliable information. Think of making a major one-off strategic decision for your business with countless unknowns, or choosing a long-term career path, or even deciding who to marry. In these kinds of scenarios, recognize that attempting overly complex, detailed analysis might actually give you a dangerous false sense of precision.
So what's the advice for large worlds?
The advice is generally to lean into robust, simple rules heuristics that strategically focus only on the most crucial, high-impact factors and ignore the potentially misleading noise. Keep it simple and robust.
And small world problems.
Contrast that with problems that are much more well-defined, stable, predictable, and where you have access to rich, reliable data. Think of optimizing a quality control process on a highly predictable production line, or calculating the optimal settings for a piece of machinery based on known physics, or playing a game like chess with fixed rules. Here, in these small worlds, more detailed, optimized strategies can genuinely pay off because the environment is stable and predictable enough to actually warrant that fine-tuning. The risk of overfitting is lower.
Okay, so first, assess the world type, large or small. What's next?
Step 2. Consider the error asymmetry. This brings error management theory directly into practical application. Ask yourself explicitly, what's likely to be worse in this specific scenario, making a false alarm, a false positive error, or suffering a misdetection, a false negative error. How costly is each type of mistake?
And based on that assessment,
You consciously calibrate your decision criteria accordingly. For instance, if false negatives are potentially far more costly, like evaluating potential signs of a serious illness during a medical screening, or assessing potential fraud in high-value financial transactions where missing the real thing could be devastating, then you should deliberately adopt heuristics or decision thresholds that are biased toward detection.
the better safe than sorry approach.
Exactly. It may be better to investigate a few benign symptoms further, false positives, than to risk letting a serious condition go undiagnosed. It's a conscious application of adaptive bias to minimize the risk of the critical miss.
And conversely, if false positives are worse.
Conversely, if false positives are the more costly or damaging error. For example, if you're in a situation like a legal setting where unjustly accusing someone of wrongdoing carries severe consequences, or perhaps deciding whether to launch an expensive product where a market flop would be disastrous, then you should actively bias your judgment toward caution and skepticism. You apply a higher threshold for action, demanding stronger evidence. This might look like an innocent until proven guilty heuristic. This demonstrates how we, as conscious decision makers, can effectively adjust our thresholds of action, deliberately mirroring the kinds of adaptive biases that evolution built into our cognition over millennia based on ancestral error costs. Makes sense. Adjust your risk tolerance based on which error hurts more. What's the next step in the guide?
Step 3. Leverage domain-specific heuristics when appropriate. If the decision involves a domain where you have genuinely deep experience, where you have reliable intuitions built up over time, or where you recognize established patterns, you can often trust those intuitions, but ideally still verify them.
Like the experienced doctor example. Exactly. A seasoned doctor might use a form of recognition heuristic for diagnosis. I've seen this specific cluster of symptoms many times before. It strongly suggests condition X. Now, while this isn't foolproof, if their extensive experience consistently shows that this particular pattern is highly diagnostic in their patient population, then it's a valid, fast, and remarkably effective heuristic to start with.
And the general recognition heuristic, when can we apply that more broadly?
The general recognition heuristic, choosing the option you recognize, works incredibly well when, and only when, recognition itself strongly correlates with the criterion you're interested in, like qualities, size, success. So if you're choosing between two products or maybe two stocks, noticing that you recognize one option and not the other can be genuinely informative if recognition in that particular domain truly tracks quality or popularity.
But the caveat is crucial here.
Absolutely crucial. You must be mindful of the ecological validity of recognition in that specific context. It works powerfully in domains like brand marketing, where a well-known brand often is, on average, a safer bet due to reputation effects. But it might utterly fail or even mislead you in other domains where recognition has no true correlation with quality, or might even correlate negatively, like maybe recognizing scandal plate companies. You need to know if recognition is a valid cue in that game.
Okay. What about decisions where one factor seems way more important than others?
That leads to step 4. Consider one reason decision-making. When you're facing a choice between options, explicitly ask yourself, is there likely one single factor or cue that dominates the outcomes? Is one consideration overwhelmingly more predictive or important than all the others combined? If the answer seems to be yes, then a powerful heuristic like take the best, which identifies that single most predictive cue and simply goes with the option that wins on that cue, ignoring everything else, can dramatically simplify your life with potentially very little loss in accuracy, or even an increase in accuracy in noisy settings.
Can you give a practical example of take the best?
Sure. Imagine you're hiring someone for a highly specialized task, say a complex programming job requiring deep expertise in a specific language. You might rationally decide that raw skill in that specific language is overwhelmingly the most predictive trait for success, far outweighing other factors like general experience or teamwork skills for this particular role. If one candidate clearly stands out on that single critical dimension, a take-the-best approach would suggest choosing them right away without getting bogged down in overanalyzing minor differences in the less important criteria.
Why is that effective?
Because it avoids diluting your decision with potentially misleading noise from those less important factors. One reason decision heuristics like take the best are especially powerful in high-noise environments, because they cut right through all the extraneous information by trusting only the strongest, most reliable signal available. They bet everything on the best horse.
Okay, but what if the situation isn't like that? What if there isn't one single dominant factor? What if you have several different factors that all seem moderately useful or important?
Great question. That leads to step 5. If no single cue clearly dominates, but you have several cues that are all moderately useful, consider using a tallying heuristic, which is also known sometimes as equal weighting.
Tallying, equal weighting. How does that work?
This approach deliberately avoids the complexity of trying to figure out the exact optimal statistical weights for each cue, or running a complex multiple regression analysis. Instead, you simply count the number of positive cues, or pros, for each option, and then choose the option that has the higher total count. It gives each positive cue 1 vote, essentially.
That sounds way too simple. Does tallying actually work well?
Surprisingly often, yes. It works remarkably well, particularly in situations where the different cues have roughly similar levels of importance, or perhaps more importantly, when you have limited data or knowledge to precisely estimate their optimal weights anyway, which is very common. Trying to optimize weights with insufficient data just leads to overfitting noise again.
And there's research backing this up.
Yes, prominently by researcher Robin Dawes. Dawes famously showed decades ago that simple equal weighting models like tallying often predict important real-world outcomes, things like academic success, loan defaults, business performance, just as well as, or sometimes even better than, statistically optimized complex regression models, especially when predicting out a sample, i.e. on new cases the model hasn't seen. The simplicity made them robust.
So a practical tip for tallying.
If you have, say, 5 criteria you're considering in a decision, like choosing a new software vendor, and you don't have a strong evidence-based reason to believe one criterion is vastly more important than the others, just rate each option on each criterion. Maybe assign a +1 for good, 0 for neutral average, -1 for bad on each, and then simply pick the option with the highest total tally score. It's fast, it's frugal, it avoids false precision, and it's often remarkably robust against noise and uncertainty.
Okay, tallying for multiple moderate cues. What else is in the practical toolbox?
Step 6 involves using checklists and stopping rules. This is a slightly different kind of heuristic. It's often about deciding when to stop searching for information or deliberating rather than how to combine the information itself.
Like satisficing.
Exactly.
Yeah.
The satisficing heuristic, which we mentioned earlier, the strategy of choosing the very first option you encounter that meets a predefined acceptable threshold or standard, can save enormous amounts of time and cognitive effort, especially in complex searches with many options.
Can you give an example of satisficing in action?
Think about buying a house again. A truly optimizing approach might demand that you meticulously research and view every single listing available in your price range across the entire city, comparing them all on dozens of features, an exhaustive search that could take months or even years and drive you crazy.
Sounds like analysis paralysis.
Totally. A satisficing heuristic, by contrast, would have you first define what good enough means for you, your essential requirements regarding location, price range, number of bedrooms, basic condition, etc. Then you simply search until you find the first house that meets all those minimum acceptable criteria and you make an offer. Done.
Why is satisficing often rational?
This rule explicitly acknowledges the economic principle of diminishing returns in search. After a certain point, the cost in time, effort, stress of continuing to search for more options likely outweighs any potential marginal benefit you might gain from finding a slightly better option. Many, if not most, successful real-life decisions, given our finite time and resources, are probably made by satisficing rather than attempting exhaustive optimization.
So practical advice for dealing with analysis paralysis.
Absolutely. When you catch yourself endlessly deliberating, stuck in analysis paralysis, consciously consider applying a stopping heuristic. You could set a firm time limit for your research. I will research laptops for 2 hours and then choose the best I've found. Or you could set a limit on the number of options you'll examine. I'll interview 5 candidates and choose the best of those 5. Then, critically, commit to actually making a choice based on the best encountered so far once that preset limit is reached. It forces closure.
Okay, one last strategy.
Yes, a very powerful one. Step 7. Actively externalize and simplify the environment. This is about recognizing that if a task environment isn't naturally suited to our evolved heuristics, maybe we can consciously transform the environment or how information is presented within it to make a simple heuristic effective. This is like bringing ecological rationality into new domains through deliberate design.
How would we do that? Give some examples.
Okay, say you're grappling with a complex probabilistic inference problem, like trying to project future sales figures based on historical data. Instead of wrestling with abstract percentages and complex statistical formulas, try converting that abstract data into concrete frequencies. Out of the last 100 similar product launches, 15 achieved this level of success in year one. Or visual case examples. This allows your naturally strong, intuitive, frequency-based reasoning to kick in more effectively.
Or using visual aids.
Exactly. Our spatial and visual heuristics are remarkably powerful. So instead of trying to compare options based on a dense table of numbers, try sketching a simple visual chart, like bar graphs comparing key attributes. This might allow you to see the best option much more clearly and intuitively than staring at the raw numbers.
This sounds like the idea of nudging or decision architecture.
It is. It's closely related to nudging and choice architecture. It's about consciously designing your decision environment or deliberately choosing how information is presented to yourself or others in a way that plays to the inherent strengths of human heuristic thinking and avoids its known pitfalls.
A practical example.
When you're faced with choosing between complex options, like different health insurance plans or investment products with lots of fine print, instead of getting lost in the dense text, try creating your own simple visual comparison. Maybe sketch simple bar charts comparing the key attributes you care about, like deductible, premium, out-of-pocket max. This externalizes the information and leverages your powerful visual heuristics for comparison, making the choice easier and potentially better.
Okay, so these 7 steps provide a really concrete framework for choosing the right approach. It emphasizes a toolbox mindset.
Absolutely. That's the core message. An expert decision maker doesn't just rely on one single approach, whether it's pure gut feeling or pure exhaustive analysis. Instead, they actively cultivate a diverse repertoire of multiple heuristics and analytical strategies, and crucially, they develop the wisdom and situational awareness to know when to deploy each one most effectively. This perfectly mirrors the idea of the mind as an adaptive toolbox. For any given challenge you face, the meta-rational question to ask is, which heuristics' underlying assumptions seem to best match the structure and constraints of this particular domain? Is my past experience in similar scenarios genuinely relevant and reliable here? If yes, my gut feeling might be a distilled, trustworthy heuristic. Or conversely, is this scenario fundamentally different from the kinds of situations my intuition evolved to handle? In which case, my gut might actively mislead me, and I should proactively use a more formal approach, external data, or a structured checklist.
Can we quickly walk through a verbal summary of that mapping, linking task features to heuristics like you described earlier?
Yes, let's verbally sketch out that mapping as a quick reference guide. Remember that this is itself a heuristic.
Okay, so if the situation is high uncertainty, few data points, a large world.
The advice is, use simple heuristics like one-reason decision-making, take the best, or maybe one n-equal allocation, if appropriate. The rationale is that complex models will just overfit the limited, noisy data. Simple rules stay robust.
If there's high noise in the cues or outcomes,
focus intently on the single most reliable cue you can identify. Deliberately ignore the minor, potentially noisy factors. Rationale. This reduces variance error. You avoid chasing random noise with an overly complex model that tries to account for everything.
If a false negative error is much worse than a false positive, missing something is catastrophic.
Then consciously bias your decision toward action or detection. Err on the side of caution. Adopt a better safe than sorry threshold. Rationale. This is adaptive bias, minimizing the risk of the critical miss as per EMT.
If a false positive error is much worse than a false negative, a false alarm is very costly.
Then consciously bias your decision toward inaction or skepticism. Raise your threshold for belief or action. Demand stronger evidence. Think innocent until proven guilty. Rationale. Avoid costly false alarms when that's the bigger danger.
If you have multiple cues, all of roughly similar importance.
Consider using a tallying heuristic, equal weighting. Simply count the pros for each option. Rationale. When weights are unknown, uncertain, or similar, simple counting often yields surprisingly robust decisions compared to trying to estimate optimal weights.
If there's one cue that is clearly far more predictive than others, a winner-takes-all structure.
Use take the best or a similar one good reason strategy. Focus laser-like on that dominant predictor and ignore redundant or weaker information. Rationale. Leverages the strongest signal, cuts through noise.
If it's a familiar experiential domain where you recognize patterns,
you can cautiously trust the recognition heuristic or your intuitive pattern matching abilities developed through experience. Rationale. Your recognition or stored patterns are likely correlated with true outcomes in that specific domain, but verified.
If the requirement is to decide quickly or with minimal cost of purchase.
Use satisficing. Set a clear, good enough standard and choose the first option you encounter that meets it. Rationale saves time and cognitive resources with often minimal loss in outcome quality, acknowledging diminishing returns to search.
And finally, if the situation is actually a very stable, data-rich, low uncertainty environment, a small world,
then more optimization, detailed analysis, or complex modeling becomes acceptable, even potentially beneficial. Rationale. When the risk of overfitting noise is low because the data is plentiful and the environment stable, incorporating additional information carefully can genuinely improve accuracy.
that mapping is incredibly useful. It's like a decision-making flowchart based on the nature of the problem itself.
Exactly. This table, or this mapping, is itself a heuristic guide. It won't cover every single conceivable situation, of course, but it provides a really rational starting point for thinking about how to think, by explicitly linking the nature of the problem you face to an appropriate style of reasoning.
And the overarching message, once again.
Fit the tool to the task. Our minds possess this incredible, evolved toolbox filled with diverse instruments, some innate heuristics shaped over millennia, some learned strategies acquired through experience. Each of these tools has specific domains and conditions where it excels. By understanding heuristics in this nuanced, ecological, and adaptive way, we can achieve two crucial goals. First, we can develop a much deeper appreciation for the ingenious design of our own cognitive architecture. And second, we can strategically refine and significantly improve our own decision-making effectiveness in the complex, challenging contexts of modern life. End of chapter recap and flashcard bullet list.
That was an incredibly practical section. Let's quickly summarize the matching tool to task guidance with our final flashcard set for the core content. Point 1.
Flashcard 1. Meta-rationality goal. The aim is to consciously choose the right decision strategy, heuristic or analysis, by matching it to the features of the task environment. It's about using the adaptive toolbox wisely.
2. The guide.
Flashcard 2. A heuristic for heuristics. 7 steps. 1. Identify environment. Large, small world. 2. Consider error asymmetry. EMT. 3. Leverage domain expertise recognition, if valid. 4. Use one-reason decisions, if dominant cue exists. 5. Use tallying, if multiple moderate cues. 6. Use checklist stopping rules, satisficing. 7. Simplify structure of the environment, nudging visuals.
3. Key mapping.
Flashcard 3. Key task heuristic mappings. Briefly recap a few core ones. High uncertainty, simple rules, robustness. High noise, tallying. Focus on best cue, variance reduction. Asymmetric errors, bias decision threshold, EMT. Multiple moderate cues, tallying, robust. One dominant cue, take the best efficiency. Familiar domain, recognition, intuition, exploit experience. Need speed, low cost, satisfies. Low uncertainty, rich data, optimization. Okay.
And the mindset.
Flashcard 4. Cultivate a toolbox mindset. Don't rely on one approach. Build a repertoire of strategies and develop situational awareness to know when to deploy each. Ask, does the heuristic fit this context?
Excellent. That gives us a clear, actionable framework. Now, let's wrap up this deep dive. Hashtag tag outro. We began this deep dive quite a while ago now with that provocative puzzle, didn't we? How could those sand Bushman trackers, armed only with traditional knowledge and their keen senses, consistently outperform high-tech scientists in the challenging Kalahari? Our journey through the world of heuristics, ecological rationality, and error management has, I hope, revealed the profound answer.
Yes, it shows that what might superficially appear irrational or simplistic can, upon deeper analysis, actually be supremely adapted, a testament to brilliant evolutionary design meeting environmental challenges.
So the core message we really want to drive home today is this. Human heuristics, all those rules of thumb, the systematic biases, the gut feelings and intuitions we carry around these are fundamentally design features, not design flaws.
That's the crucial reframe. They reflect a mind that was meticulously shaped by the relentless pressures of natural selection to solve the most pressing real-world problems, finding food, choosing mates, navigating social landscapes, avoiding dangers all under stringent constraints of limited time, incomplete knowledge, and finite computational power.
Our ancestors didn't need a brain that could compute perfect probabilities in some abstract mathematical space.
No. They desperately needed one that could reliably catch the proverbial rabbit, secure vital social alliances, and deftly avoid the venomous snakes hiding in the grass. And in those absolutely vital pursuits, fast and frugal heuristics made us smart enough, efficient enough, to not just survive, but to truly thrive and eventually dominate the planet.
Now, it's important to reiterate, none of this is meant to suggest that humans are infallible or that every single gut feeling we experience is automatically golden and should be blindly followed. Far from it.
Absolutely. Rather, This entire perspective beautifully reframes our apparent cognitive limitations, not as inherent failures or bugs in the system, but often as the necessary flip side of highly specialized strengths. We constantly and often wisely trade theoretical optimality in abstract hypothetical scenarios for robustness and effectiveness in messy, everyday, high-stakes situations.
And recognizing that inherent trade-off is actually incredibly empowering, isn't it?
It really is. It means we can perhaps be much kinder, more understanding towards our own brains. Instead of constantly lamenting their perceived biases as imperfections we need to stamp out, we can start to marvel at their ingenious economy, their evolved wisdom. And then from that place of understanding, we can strategically correct or consciously supplement them precisely when we recognize we're stepping outside their effective, evolutionarily designed operational range.
You mentioned Steven Pinker's quote about common sense.
Yes. Pinker aptly noted that common sense itself, our everyday intuitive reasoning, is fundamentally an organ of evolutionary design. So, when we learn to plan better by consciously acknowledging and accounting for our innate optimism bias, or when we make a sound decision more quickly by intuitively knowing when to stop gathering more information, satisficing, we are not fighting our nature. Instead, we are embracing our evolved design and learning to work harmoniously with it.
So, for you, our rationalist listener, who often seeks precision, logic, and optimal solutions, the takeaway from this deep dive is perhaps particularly profound.
I think so. It suggests that true rationality, perhaps counterintuitively, isn't solely about performing more complex math, gathering ever more data, or attempting to banish all forms of intuition from our decision-making.
What is it, then?
It's more about cultivating the wisdom, the meta-rational skill, to deploy the right form of reasoning, whether heuristic or analytical, for the specific situation at hand. Sometimes, yes, true rationality will indeed look like a complex, meticulous calculation, perhaps involving sophisticated statistical models or logical proofs. But other times, arguably more often in the large world we inhabit, true rationality will look exactly like a simple, elegant rule of thumb that consciously and strategically ignores 90% of the available data to laser focus on the crucial 10% that actually drives the outcome.
And the real wisdom lies in knowing which approach is which for which problem.
Precisely. It takes wisdom to know which is which. By appreciating heuristics as these incredible evolutionary design features, not just as flaws, we gain access to precisely that wisdom. We learn to recognize the specific conditions under which thinking fast using heuristics can decisively outperform thinking slow with laborious analysis, and just as importantly, vice versa. We come to understand that even pervasive biases, things like overconfidence or loss aversion, possess a deep underlying evolutionary logic. And understanding that logic allows us to manage them within ourselves and when observing others with greater empathy, precision, and effectiveness, rather than with mere scorn or frustration at perceived irrationality.
So in closing, the study of heuristics as adaptive, finely tuned tools really bridges that critical gap between understanding our inherent human nature and pursuing truly rational action in the world.
Yes, it tells us that to be rational in a profoundly human way is perhaps not primarily about trying to emulate a cold, logically perfect computer, but rather about becoming an expert artisan, skillfully balancing and judiciously deploying our various mental tools, knowing our inherent limits, yes, but also celebrating and leveraging our astonishing evolved strengths.
Think back one last time to our Sam Bushman tracker.
He doesn't compute complex differential equations using satellite data to chase his prey. He uses a few simple yet incredibly powerful ecologically tuned rules like, if the print is deep and the stride short, the animal is tired and likely close. He trusts his heuristics, honed over generations in that specific environment, and he feeds his family.
And we, navigating the often overwhelming modern jungle of information and decisions.
We can do similarly. We can learn to choose smart rules for recurring problems, develop the self-awareness to know when to trust them implicitly, and cultivate the wisdom to know when the environment has changed and it's time to switch tools, perhaps engaging more deliberate analysis or seeking external data.
Our evolutionary heritage provides us with this remarkable, intricate toolbox.
And science, coupled with thoughtful introspection learning, provides us with the invaluable map for skillfully using it. And that powerful synergy, that dance between our evolved instincts and our conscious understanding, lies our absolute best hope for consistently making decisions that are not just rational in some abstract theoretical sense, but are truly successful, adaptive, and impactful in practice, just as evolution, in its own way, intended.